Hello students, let's get started with a session on calculus. In this session we are going to learn about limits and continuity. If time permits, we're going to move on to differentiability as well. Let's get started. First of all, the scope of this session is calculus of one variable only. So we are going to stick to calculus of one variable alone. What do we mean by calculus of one variable? That means all the functions that we are going to consider will have only one independent variable. Just to give you an example, let's say I have something like y equal to x square plus 3. In this function, there is one independent variable, x. Here is the independent variable. So these are the kind of functions we're going to stick to. There can be other functions having one independent variables like let's say y equal to cosine of x. This also has one variable only. We're going to stick to these kinds of functions only. We're not going to study about calculus of more than one variables, like the functions that have more than one variables, like two variables or three variables. Some examples of such functions which we are not going to cover in this session is, let's say we have y equal to x square minus z, or y equal to x square minus z square plus 23. So these here, if you see, we have two independent variables, right? Two independent variables. Now these are the functions we are not going to consider today. Okay, this is not in our scope. We're just going to stick to calculus of one variable. I hope this is clear to everyone. All right, so let's get started and let's find out the value of a function. Value of a function. First, what is the limit of a function? We're going to get into that a little later. Before that, we all know how to find the value of a function, right? If, for example, the function is this, fx is equal to sine of x. Don't we all know how to find the value of f of x? If I give you the value of x, so at x equal to pi by 2, can you all give me the value of sine of x? The sine of x's value is going to be sine pi by 2. That's going to be the value of f of x at x equal to pi by 2, right? What is sine pi by 2? Well, pi by 2 is measure of angle in radians. Sine pi by 2 can also be written as sine 90 degrees if you want to write it in degrees. Sine 90 degrees, we all know the value is 1. Even from the graph, you're able to see that. See, when the independent variable takes the value pi by 2, the dependent variable, that is f of x or y, takes the value 1. We all can see that, right? So finding the value of a function is easy. We all have seen that, how to find these values in junior classes. Today's focus is going to be on limits. What are limits and why do we need them after all? Okay, let's try a couple of more exercises on finding the value of a function. This time we have an interesting function. It's something like this. The function is sine of x upon x. Try finding out the value of this function at x equal to 0. Just try it out. Take a couple of minutes, pause this video and try it out on your own. I hope you've tried it out, and you would see that there is a problem with this. Now, if we try to find out the value of f of x at x equal to 0, I can directly write that as f of 0. So if I have to find out f of 0, that's going to be sine of 0 upon 0. Well, sine of 0 is 0 upon 0. Now this is interesting. I can't really find out the value of 0 upon 0. The exact value of something very, very small divided by 0, or 0 divided by 0. This is something which is not defined. No one knows the answer to this. So what happens now? We can't, we definitely know that we cannot find the value of sine x upon x at x equal to 0. So value of this function is difficult to find at this point at least. Let's try out one more question. One more function. We have y equal to this. Now I want you to find out the value of this function at x equal to 2. So what you have to do is, wherever you see x, you substitute 2 there. Okay, you substitute 2 there. Pause the video, try it out, and then restart it again. I'll be substituting the value 2 everywhere, wherever there was x, and I'll choose a different color this time. Let's choose blue. Yeah, so 2 minus 2, and here also 2 minus 2. What do we have? E to the power 2 minus 2, that is e to the power 0 minus 1 upon 2 minus 2 is already 0. Again, we encounter a similar problem. E to the power 0 is 1, so we have 1 minus 1 on the top and 0 at the bottom. So overall we have 0 upon 0. Again, the same problem. I do not have a specific value. I have an expression which is not defined in mathematics at all. Such expressions are called indeterminate forms. So yeah, we just saw that it was difficult to find out the value of some functions. I gave you a couple of examples. The value of some functions at some specific values. For example, the value of sine x upon x at x equal to 0, we couldn't find the exact value. Similarly, the value of the second function, e to the power x minus 2 minus 1 upon x minus 2, the value of this function at x equal to 2 was difficult to find. Why? Because when we tried putting in the values of x equal to 2 here, we saw that I'm getting something which looks like this. This is 0 upon 0, and we all know that anything divided by 0, any number divided by 0 is not defined in mathematics at all. We have many different forms like these, like 0 by 0, which are not defined in mathematics. We call those as indeterminate forms in mathematics. What are some of those forms? Let's look at some examples, okay? Infinity by infinity. Now, this thing is also not defined in mathematics. So if you encounter somewhere infinity upon infinity and someone asks you what the exact value of that is, we can't really say. And that is why if we cannot determine the exact value, it's called the indeterminate form. 0 by 0 is another such indeterminate form. Similarly, we have infinity minus infinity. Now, it would be tempting to say that, isn't this equal to 0? Yeah, we know that 5 minus 5 is 0. So why not infinity minus infinity? Why can't I say that it's 0? The problem is this, that infinities are something that can never be equal. See, we can't really say that one infinity is equal to another infinity. All we know is that infinity means something very, very large. Now, it might be possible that this infinity is larger than the second infinity, or the first infinity is smaller than the second infinity, and that would change the answer. And that's why we can't really be sure what these numbers actually are. We just know that these are very, very large numbers, that's all. And that's why it's indeterminate form. Okay. uh, yeah, moving on to the other indeterminate forms, let me quickly wipe the screen and so we can start fresh. Okay. Okay, there are some more indeterminate forms like 0 to the power 0. Now, we've studied before that any positive number, any whole number, natural number, or integer, when raised to the power 0, gives you 1. But 0 raised to the power 0 cannot be 1. Now, there's a whole uh, uh, process to prove this, why this cannot be equal to 1. We'll do it some other time. For now, just remember that 0 to the power 0 is also an indeterminate form. There is no specific value for this expression. Similarly, 0 multiplied by infinity, it's an indeterminate form. Infinity raised to the power 0, again an indeterminate form. 1 to the power infinity, again an indeterminate form. So, whenever by putting some values like x equal to 2 in the original function, we get an indeterminate form, we are lost. Basically, we cannot tell anything about the function. We cannot tell what value the function takes at that point. Well, we can't really talk about the value of that function at that point, but we can still analyze the function a little bit using limits. What is the limit of a function? In simple words, the limit of a function at a given point is the value that function approaches as our input gets closer and closer to that specific point. With the help of an example, let me explain to you once more. See, here I have a graph of sine x upon x. This is the graph of sine x upon x. If I ask you what is the limit of this function as x approaches 0. So as I move towards 0, now there are two ways to move towards 0, from the left and from the right. See, from this side and from this side. Let's say I start moving from the left side. As I start moving, inching closer and closer to the 0, I find the value of this function is somehow, it's going in this direction. It's approaching something. We'll figure out what that number is, where that function is approaching later. But at least it's approaching some value. If I move towards this 0, independent value, independent variable 0, the value of independent variable 0, if I move from the right side towards 0, the value of f of x, which is sine x upon x, the value of this function is again approaching some point. Okay, so that whatever the value I'm getting here, that is the limit of this function. That is the limit of this function. So what is the limit of a function f of x? The limit of f of x at a given point x equal to a is the value that function f of x approaches when we approach a. Okay, that's what limit is. So as we move closer to a, that the value of that function also moves closer to some value. That value is called the limit of this function f of x. Okay, we'll try to understand it with the help of some more examples. Uh, but one thing you should appreciate that, see, sine x upon x is a function, the exact value of which we were unable to find. Irrespective of that, we can still analyze this function by looking at its limit. We can still see the behavior of this function, we can still analyze the behavior of this function by looking at its limit. What else is limits used for? All right. Why should we study limits at all? Well, to understand, first of all, is to understand the behavior of a function as it approaches a certain value. We just saw sine x upon x was a function. As x approached the value 0, sine x upon x also approached a certain value. We haven't yet found out what value the function approached. We'll do that later. But at least, we know that limits help us understand the behavior of a function. It cannot give us the exact value, but it tells us, that there is some value to which the function gets closer. So it helps us approximate. The second thing where limits are used for is to understand the nature of the function. Now, whether it is a continuous function or a discontinuous function, whether it is a differentiable function or a non-differentiable function, and so on. So limits also help us understand the nature of the function. What else? See, when we learn about derivatives and integrals, I'm sure you know that calculus is broadly divided into integral and differential calculus. So, uh, when we try to understand derivatives, what do we mean by derivatives? What do we mean by integrals? The understanding of limits is very important because derivatives and integrals are defined using limits. If we don't understand limits, we won't understand differentiation, we won't understand integration. So from the syllabus perspective also, understanding limits is very critical to understanding calculus. I hope we all understand this. Okay, let's come to the proper definition of limit of a function. Now, the limit of f of x as x approaches a certain value, x naught, okay? The limit of f of x as x approaches x naught is L, that is, this is how we write it, okay? So limit of f of x as x tends to x naught is L. This is how we read it. Here's a very famous epsilon delta definition of limits. Let me explain this to you. When do we say that the limit of f of x is L? When x approaches x naught. When we can find out that there is some epsilon, this is infinitely small, or we also call it infinitesimally small. Infinitesimally small. That means very, 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 very small. So we say that the limit of a function f of x is equal to x if there is a very, 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 very small epsilon. That means a very, very small positive number exists such that the distance between x and x naught, that means the value, let's say this is our x naught, okay? The distance, if I'm here, currently I'm here at x, okay? If the distance between x and x naught is very, 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 very small, but positive, of course, distance has to be positive. The distance between f of x and the limit, that is the number, this L, is also very, very small. Only then we say that the limit of f of x is equal to L. Only then we say that. So the value of, let's say, whatever is the value here, okay, and let's say this is f of x. Uh-huh. The actual, the distance between this number L and f of x, this is also very small. So that's what we mean by uh, limit of a function. Once again, the formal definition of, let's understand the formal definition of limit of a function. This is a very classical, very important epsilon delta definition of limit of a function. Let's try to understand it once more. Let me remove all these markings and yeah. Okay, let's try again. Limit of a function f of x as x tends to x naught is equal to L when there exists an epsilon and there exists a delta. Epsilon and delta are nothing but these are very, very small positive numbers. When there exists epsilon and delta such that x minus x naught, the modulus of x minus x naught is basically the distance between, it represents the distance between x and x naught. Okay, so the distance between x and x naught is very small. This implies that the distance between f of x and this number L, this value L, is also very small. Okay, so that's what limit is. So as we are approaching x naught, as the input is approaching x naught, the output is approaching L. If that's the case, we say that limit of the function f of x is L. That's it. Okay, so put very simply, as x gets closer to x naught, f of x gets closer to L. In that case, we say that the limit of the function f of x is equal to L as we approach x naught. All right. So here's an example. Let's try to find out the limit of this function. Okay. This function is, as we can see, x square minus 4 by x minus 2. Here the function is written. Okay, so this is the graph of this function. Now if I ask you find the value of this function at x equal to 2, would you be able to do that? We can't really. Okay, we can't find the value of this function at x equal to 2 because you can see that at x equal to 2, this function is undefined. This function is not defined there. So how can you find the value of this function at x equal to 2? But you can still find the value of, you can still find the limit of this function at x equal to 2. Because all you need is which number is it approaching. Which number is it approaching, and that would be the limit of the function. We'll see how to find the limits of the function, of different types of functions later in the class. Today, the aim of this session is to give you an understanding of what is limit, why do we need it, and how it helps us understanding continuity or the nature of a function, whether it is continuous or discontinuous. Let's move on. Now, I have a function f. Okay, so it's represented by this thing, small f. Okay, I have a function and I want you to find out the limit of this function at 3 different points. Now, before we start with this exercise, let me tell you one thing. See, earlier I told you that there are 2 ways to approach the limit of a function. One, you can approach it from the left side like this, or you can approach it from the right side. It's very important. So the limit of a function exists only if you get the same number by approaching it from the left side and by approaching it from the right side. Once again, I'll repeat. See, let's say I find limit of this function, limit of f of x, when x approaches 2 from the left side. That's why that minus sign is there. Okay, so this will show you the limit of this function when we are approaching it from the left side. Then let's say this thing, this blue thing represents limit of f of x when we approach x, or when we approach 2 from the right side. So 2 plus means slightly bigger than 2, or when we are approaching here, when we are here. So this place is 2 plus, and this green dot, this place is 2 minus. Okay, so when do we say that limit of a function exists? When you get the same number by approaching it from the left side and from the right side. When you get the same value by approaching it from the left side as well as from the right side. And that's what is summarized here. So the function f has a limit, this is a number, okay, has a limit L as x approaches the value a, if and only if you get L from both the sides. Okay, you get while you're approaching from the left hand side, we call that left hand limit, and we call this thing as right hand limit. So only if your left hand limit and your right hand limit are the same, only then you can confidently say that okay, there is a limit of this function, there is a value where this function approaches. All right, with that understanding, let's try to find out whether limit exists or not for these values, for this function small f. Let me remove all these markings so that we have a clean slate and we can start working on it. All right, so here's a very odd looking function. It's been defined along the x-axis, so the domain seems to be all real numbers. So this point 2 is included, this point is excluded. I hope you all understand what a hollow circle and a solid circle mean on graphs. You also see that the function is not defined at the point 4. So f of 4 is not defined. Okay, it's not defined at all. Okay, so we've scanned the graph, and let's find out what limits we need. So the first question is find the limit of this function at x as x approaches 6. Okay, 6 is this. As x approaches 6 from the left hand side, from this side, if you approach it from this side, you're approaching this value, and if you're approaching from this side, you're again approaching the same value. And what value is that? 1. So the limit of this function is 1. Pretty simple. Even if I asked you what is the value of this function at x equal to 6, it would come out to be the same. This is also the value of this function at x equal to 6. Okay, this one was pretty easy. Now let's look at what is the limit of this function at x equal to 4. Now 4 is an interesting point. We just discussed that this function is not defined at x equal to 4. So what to do now? Okay, let's see. That's fine. Even if a function is not defined at a value, we can still find the limit of its function. Let's see. If we approach this function from the left hand side and we try to find out the left hand limit, what value is this function approaching? I can see it's approaching the value 3. Okay. If we try to approach this point 4, x, as x tends to 4, from the right hand side. Now let me pick another color. If I try to approach it from the right hand side and I want to find the right hand limit, what value is it approaching? What value is f of x approaching? It's approaching the same value 3. So what do we see? That the left hand limit is equal to the right hand limit, and it's actually equal to the value 3. So you can confidently say that, okay, when x approaches 4, the limit of this function f of x approaches, or the limit is 3. Okay. Now we have one more question to answer. Let's clear things up. Let's wipe the slate clean and get started with the third question. All right. As x approaches 2, now there are two ways to approach this number. One is from the left side, the other is from the right side. Now, if we try to approach this from the left hand side, I'll have to walk along this line. This will give you the left hand limit. Can you tell me what is the left hand limit? We can see that the left hand limit is 2. Okay, let's try to approach this number from the right hand side now. You can only walk along the graph, okay? You can't walk wherever you want if you want to approach that point. All right, so let's take a different color now, and this time we want to approach this number, this x equal to 2, from the right hand side. That means from this side. If I want to approach it from this side, what value am I approaching? So the right hand limit you can see is I'm approaching 5 if I approach x equal to 2 from the right hand side. Is the left hand limit coming out to be same as the right hand limit? The answer is no. That means one and one thing only, that limit of this function does not exist at this point at x equal to 2. So see, same function, the limit exists at x equal to, at when x tends to 6. X tends to 6. This is how we read it, okay? Tends to, or x approaches 6. Similarly, when the limit of this function also exists when x approaches 4 or x tends to 4. The limit also exists then. But does the limit of this function exist at x equal to 2 or as x approaches 2? Does the limit of this function exist? The answer is no. For limit to exist, you have to get the same value from both sides. Okay, so what did we learn? We learned that the limit of a function exists only when the left hand limit is equal to the right hand limit. Okay, so yeah, it's a very important learning. It's a very important point. Please note it. Okay, let's try one more example. I have a very similar graph than the last one, and we're going to find out the limit of this function g of x at different points. So g of x, this is the graph of g of x. Okay, it's defined along the domain is all real values of x. This is x-axis, this is y-axis. Okay, so find limit of g of x as x tends to -1. Can you tell me the answer? And you also have to find out the limit of g of x as x, there, let's look at some more critical points. As x tends to 0, you find this value. You also tell me what is the limit of g of x as x tends to this number 1. Anything else? Okay, let's try to find out the limit of g of x at x equal to 2 as well. So 4 questions. Pause this, pause this video, think for a while and try to write down all the 4 values. Take 5 minutes, write down all the values, and then unpause the video to check out the answers. Okay, I hope you have attempted these 4 questions. Let's try to figure out the values. Let's try to find the answers. At when x approaches -1, so there are 2 ways to approach -1, from the left side and from the right side. If you're approaching it from either side, you're going to get the same value, and that value is this. So the limit of this function at x equal to -1 is 3. Let's look at what happens when x approaches 0. Alright, when x approaches 0, interesting. Let me pick another color. Yeah. When x approaches 0, let me make the line a little thicker. Yeah. When x approaches 0, there are 2 ways again to approach 0. One from the left side, this is your left hand limit. The other from the right side, right hand limit. Now, approach it from whichever way, whichever side you want. It's approaching this value only. This value, although it's not written, it's 4. Okay, so that's your answer. Okay, what is the value of this function, exact value of this function at x equal to 0? The exact value of this function at x equal to 0 is this. Okay, we are not bothered about the exact value right now, we're just finding the limit. Which value does this function seem to be approaching when we are approaching 0 from either sides? When we are approaching 0 from either sides, it appears that the function will arrive at this point labeled as 4. Although later we find out that the exact value is 1, that is not of consequence right now. You can ignore that. Move on to the third question. All right. So what happens when x approaches 1? What happens to the limit of this function? Let's see. Approach x from the left hand side, see what you're getting. Approach x from the right hand side, see what you're getting. Approach 1 from the left hand side, if I do that, I'll get this. This is 3. So I see that the left hand limit is 3. Try approaching this point from the right hand side. Now if you approach it from the right hand side, right hand limit is, what is the right hand limit? It's this number, 2. See, left hand limit is 3, right hand limit is 2. Are they the same? Of course not. So the limit does not exist. We just saw, right? If the left hand limit is not the same as the right hand limit, you can claim that the limit does not exist. Simple as that. Finally, let's figure out what is the limit of this function g of x when x approaches the value 2. Okay, when x approaches the value 2, we can approach this value from two sides, from the left hand side or from the right hand side. Whichever way, whichever side you approach this point, you're going to get this value only. So this. How many of you got all the four answers correct? Now, if you've got all the four answers correct, you have perfectly understood the concept of limits. When do we say that limit of a function exists? When do we say that the limit does not exist? Okay, let's move on. And I told you that I'm going to transition to the nature of the function, like figuring out the nature of the function using limits. Now, one of the natures of a function is like whether the function is continuous or not. What do we mean by that? So, a continuous function, for a continuous function, the limit exists. That's one criteria. The other criteria is that the value of the function, the exact value of the function, is also same as the limit. Once again, see, if I ask you to find out the limit of f of x at x equal to 1 or as x tends to 1, can you tell me the limit of f of x as x tends to 1? You try approaching this point from the left side and from the right side. What do we get? In both the cases, the value of the function seems to be approaching this point. So the limit of f of x is this. But what is the value of f of x here? At 1. What is the value of f of x at x equal to 1? The function is not defined at this value. It's not defined. Okay, let's look at the second function, which is g of x. It looks very similar to the first function. So we can say that limit of g of x when x tends to 1, with the same logic as before, that this limit is going to be 3. And what is g of 1? G of 1, this time it's defined. We can see that g of 1 is defined as this number. It is this. Okay. All right. Let's look at the third function. Let's look at the third function, which is h. Can you tell me what is the limit of this function h of x as x approaches 1? Use the same logic, it's again 3. See, approach it from this side or from this side, you're going to arrive at the same number. So it's 3. All right. What is the value of h of 3? Sorry, h of 1. What is the value of this function h of x at x equal to 1? This time, this function is defined. You see this circle, it's filled, it's a solid circle. The value is also 3. See, the limit exists and is equal to 3. The value of the function exists and is equal to 3. Only in these cases, only in third case, we can claim that the function in question is continuous. It's continuous. So h of x is a continuous function. All right. So that's all about continuity. Not all about continuity, at least the start of it. So what do we mean by a continuous function and a discontinuous function? So if the limit exists but is not equal to the value of that function, it's not continuous. It's a discontinuous function. And there are different types of discontinuities. So we'll learn about those things later. Okay, today we focus on limits and limits only. Let's move on and see some properties of limits. Okay, I'm going to stop. I'm going to pause the class here. We're going to take this up in the next class. Okay, we're going to look at some properties of limits. There are different properties. I've listed a few. You can go through your textbooks. Come prepared for the next class. You will understand much better. Okay. Thank you so much, students, for joining this session. I hope you learned something today, and some concepts got cleared related to limits. Thank you so much. Bye bye. Take care. Have a nice day.